Good morning. In the last class, we have seen the concept of wet etching. The wet etching before coming to the wet etching, we have seen the concept of bulk micro manufacturing. We have seen the concept of bulk micro manufacturing. The bulk micro manufacturing or micro matching, it involves the removal of material from the substrate. Basically, it is a removing concept. So what I need to do is I need to remove the unwanted part and I need to maintain the required part. So for that, either physical or chemical technique, maybe a dry etching or wet etching is possible. And if I come to the concept of wet etching, and if I go for the wet etching, there are different types of etchant. There are different types of etchant that are available. So now if I take an isotropic material, the common etchant is HNA. So this we have seen in the last class. And what is HNA? HNA is nothing but hydrofluoric nitric acidic. That is HNA. And if my material it is anisotropic, the concept is anisotropic etching. So now there are different types of the etchants available. So that is nothing but potassium hydroxide, ethylene diamine pyroatacol, commonly called as EDP, and methyl ammonium hydroxide, commonly called as TMAH. And how this is done? So now any one of these etchant, it can be HNA, KOH, EDP, or TMAH. So they are mixed with the water in the ratio of 1:1. Okay. So now this is very important now. So now if I take silicon, the silicon is the material, and if I take the KOH and the etchant, my etch rate is 0.25 to 1.4 micrometer per minute. And if I take silicon dioxide, the same etchant, my etching rate is 40 to 80 nanometer per hour. And similarly, if I take silicon nitride, same etchant KOH, my etching rate is 5 nanometer per hour. So that means with the same etchant, etching rates are different. The etching rates are different. So now what I can do is, I can now define the selectivity ratio. So the selectivity ratio is nothing but the etching rate of silicon compared or divided by the etching rate of silicon dioxide with the same etchant. And if I do that, I'll get the selectivity ratio. So the etching rate of silicon divided by etching rate of material using the same etchant. And out of this now I got, so if out of that I got the selectivity ratio of silicon dioxide with KOH, it is in the ratio 10 to the power 3. Similarly, silicon dioxide with TMAH 10 to the power 3 to 10 to the power 4. And similarly, silicon nitride with the KOH, I got 10 to the power 4. TMAH 10 to the power 3 to 10 to the power 4. So what I can conclude here is, higher the selectivity ratio, better the mass material is. So that means if I am going for the wet etching, if I am going with the silicon material, silicon dioxide and silicon nitride can be used as the mask. It can be used as a masking material. You can see the example here. So now say I want to maintain this layer, or I want to maintain this part. I want to maintain this part, or I want to maintain this structure, or I want to maintain this layer. If I want to maintain this layer, if I am going for the wet etching, what I'll do is I'll take any one, the KOH, EDP or TMH, any etchant I'll take. I'll put the entire structure into the chemical solution. can be HNA, EDP or TMAH. So under that condition, what happen is, so now I want to mask this layer so that finally I want to retain the structure or I want to retain the shape. So I'll take the mask as silicon dioxide or the silicon nitride. So they are acting as a mask now. They are acting as a mask. Okay, so I'll put this into the chemical solution. So what will happen is, after some time, the whatever the unwanted part, say if I want to remove this part, so unwanted part will be removed. So unwanted part will be removed. So this will be my final structure. So I'll be removing the unwanted part or unwanted layer. So it is perfectly in the required shape. So it is ideal etching. So something deviation from the required shape, it is undercutting, under etching and undercutting. Okay, so this is with the help, this is nothing but my wet etching, and I started the process. Now somewhere I want to stop this process, so the wetting process. So that means finally that this part is removed. After the process, the unwanted part is removed. The unwanted part is removed. So now I want to stop this process. So now if I want to stop this process, so what I need to do is, now there are two concepts again. So there are two concepts. So one, it is the Doppler controlled etch stop, and other one is the electrochemical etch stop. So in the Doppler controlled etch stop, what they do is, so they dope. Okay, so the silicon is doped with silicon substrate. It can be with the boron for P type and silicon for N type. So that means they are doing the doping process. And in the electrochemical etch stop, what they do is they introduce a PN junction in the process. So that means if this is the process, so somewhere here, so somewhere to this junction, they produce a PN junction. So PN junction is introduced. So by introducing a PN junction, so this process gets stopped. So that is nothing but the etching stop. So that is electrochemical etch stop. Okay, so now if I come to the dry etch, so I want to do the dry etching. Okay, so now dry etching. Now dry etching, it involves the removal of substrate material by gaseous etchant. It is by the gaseous etchant. So without the chemical, without any chemical or without any the rinsing process. Basically, there are three different types of etching techniques. One is the plasma etching, and second one is ion milling, and third one is the deep reactive ion etch. Deep reactive ion etch. So what I will do is, so first I will take the plasma etching. I will take the plasma etching. Okay, so now plasma. Now first, why I need to study now what is plasma. So plasma, it is nothing but it is the ionized gas, or it is a gas of the ions. So it can be artificially generated by heating a neutral gas or subjecting it to a strong electromagnetic field to a point where the ionized gas becomes electrically conductive. Okay, so now what is plasma? So plasma is nothing but it's a gas of the ion, or it's an ionized gas. It can be artificially generated by heating a neutral gas or subjecting it to an electromagnetic field to a point where the ionized substance becomes electrically conductive. Okay, so that is my plasma now. So I'll be artificially generating plasma, and whatever the plasma generated, I'll add a chemically reactive gas. I'll add a chemically reactive gas, So the chemically reactive gas, it is usually Freon 12. It is Freon 12. So what I am doing is, so first I am generating plasma. I am generating a plasma. Okay. Second, I am adding a chemically reactive gas. It is Freon 12. Usually Freon 12. Now what will happen? So what will happen is, now this is very important. I'll go to this figure now. So now what I am doing is, so now I am generating a plasma. So this is usually with the help of radio frequency source. And next I'll add a reactive gas. I'll add a reactive gas. So that is nothing but Freon 12. Freon 12. Okay. So now what will happen? This is very important. Now, so now in this process, so that means generating a plasma, adding chemical reactive gas. What will happen is, the reactive gas produces reactive neutral. So the reactive gas, it produces the reactive neutral. The reactive gas produces reactive neutral. This reactive neutral, so you can see here what are N are reactive neutral. They bombard the side walls. Okay, so they bombard the side walls of the target. So this is my target. So target in the sense, I want to maintain this layer, or I want to maintain this structure. I want to maintain this structure, and I want to remove this, the unwanted layer, or this is not desired for me. So I want to remove this layer. So for this what I'll do is, now whatever the reactive neutral generated, they bombard the side wall. They bombard the side wall, and at the same time the charged ion. So now this is the charged ion. So this place is the charged ion. They bombard the normal surface. They bombard the normal surface. Okay, so see here, the charged ion, they're not bombarding the target surface, they bombard the normal surface. Okay, whereas the neutral gas, reactive neutral, they bombard the side wall, at the same time they bombard the normal surface also. The charged ion, they bombard only the normal surface. So what will happen is, because of this, the high energy reaction causes the local evaporation here. It causes the local evaporation, thus result in the substrate. Material. Okay, so now this is the process of plasma etching. So now this concept is dry etching. Okay, so now what I need to do here it is, so I need to generate plasma. And what is plasma? So plasma is nothing but neutral ionized gas carrying large number of free electron and positive charged ion. So plasma contains large number of free electron and positive charged ion. And next, adding a chemically reactive gas such as Freon 12. And the process, and this process now, what happen is, during this process, the reactive neutral generated, they bombard the side wall as well as the normal surface, whereas the charged ion, they bombard the normal surface. Now, because of this, the charged ion has high energy content, and because of this, the local evaporation happens here. The local evaporation happens here, and finally, the removal of substrate material. So whatever the substrate material is there, it will be removed. So this is the process of plasma etching. So this is very important from exam point of view. Okay, so what I'll do is plasma artificially generating with the help of radio frequency source. Next, I'll add a chemically reactive gas, usually freon 12, to the plasma. Now the reactive gas produces reactive neutral when ionized with the plasma. The reactive neutral bombard the target on the side wall as well as on the normal surface, whereas the charged ion bombard only the normal surface of the substrate. So etching of the substrate material is accomplished by the high energy ion in the plasma bombarding the substrate surface. Okay, so this is the process now. Generating the plasma, adding the reactive gas, reactive chemical, usually freon, and during the process, reactive neutrals are generated. They bombard the side wall, and at the same time they bombard the target normal surface also. The reactive neutral, they bombard the side wall, they bombard the normal surface, whereas the charged ion, they only bombard the normal surface, and because of the high energy content of the charged ion, the local evaporation happens here, and because of the local evaporation, the substrate, okay, so the substrate will be removed. The substrate will be removed. So basically because of the evaporation. So the high energy of the ion, there's a local evaporation, and the result is the removal of substrate material. Removal of substrate material. So this is the process of plasma etching. Okay, so now the high energy reaction causes local evaporation and thus result in the removal of substrate material. And the plasma rating, it is usually 2 micrometer per minute. Usually 2 micrometer per minute. Okay, so next is the deep reactive ion etching. The deep reactive ion etching. So we have seen the plasma etching. And next we need to study the deep reactive ion etching. So why deep reactive ion etching? Okay, so now say I have seen the plasma etching. So the plasma etching, what I need to do here is, what I need to do here is, say I want to maintain shape like this. I want to maintain a shape like this. For that I'll mask this layer, and I want to remove this substrate material here. I want to remove the substrate material here so that my final shape will be something like this. This is my final shape. So this is my final shape. So this is my final shape. Okay, after removing the substrate material. So now during this process, I may not get a shape perfectly like this. So what may happen is, during the process, it may go like this also. The substrate will be removed something like this. Will be something like this, or something like this also it may happen. right? So I wanted this shape. I wanted this shape. I wanted something like this shape. I wanted something like this shape and this shape. Because of the during the process, my etching may not be perfect, and I can get a shape something like this. So which is shown in the blue line. That should not happen. So that should not happen. Why? Because say say I'll take this as something actuator. This is something like an actuator. This is something like an actuator. So say I am doing the electrostatic actuator, electrostatic actuators. Under that condition, so this I connect it to the positive supply, and this I connect it to the negative supply, and as a result, so there is an force of attraction between these two electrodes, and something what I can use, what I can use is, this is something like something used for the micro gripper. So holding something, a small, say small paper. Okay, so electrostatic actuation I'll do, micro gripper, something like micro gripper, and I'll hold a small paper between these two electrodes. So for that, what I want a perfect shape. I want a perfect shape like this, and this perfect shape I may not get in all the condition, in all the process. So for that, what I need to do is I need to go for the deep reactive ion etch. So the deep reactive ion etch. Okay, so now this is the process I have explained. So now during the process, what may happen is the substrate material, the substrate material will be removed like this. It will be removed like this. So that means under this condition, there is an angle theta. So angle theta formed. So what I wanted a perfect shape, a perfect square shape I wanted. Should I get a shape like this? So that was my aim. I wanted a shape like this. But during the process, during the process, I got a shape like this. I got a shape like this. I got a shape like this. So that means there is an angle theta. So now this angle theta, I want to make it as 0. This theta, I want to make it as 0. So for that, what I need to do is, I need to go for deep reactive ion etch. The deep reactive ion etch. So this is the process of making an angle theta 0. This is the process by which I'll make an angle theta 0. So what I need to do here, again I need to do the dry etching. So again what I'll do is, I'll go for the plasma etching. I'll go for the plasma etching, no difference. I'll go for the plasma etching, and again I'll add reactive gas. I'll add reactive gas. I'll add reactive gas. So here this is very important. So I need to generate a plasma source, that is with the help of the radio frequency. Radio frequency. So next I need to add a reactive gas. So here very important is, in the plasma etching we have added freon 12. In the plasma etching we have added freon 12, but in the deep reactive ion etch, so what I need to add is, I need to add fluoropolymers. The reactive gas is nothing but fluoropolymers. So why? Because so now, okay, so now this, as usual, I'll mask and at the same time I need to mask here also. I need to mask this surface also. I need to mask, sorry. So I need to mask here and I need to mask here so that my angle theta becomes 0. Anyhow, I'll be masking this layer. I'll be masking this layer. So this is the normal process. But addition is masking this layer or this surface. So for that, what I need to do is I need to add reactive gas to the plasma, and that reactive gas is nothing but it is fluoropolymers. It is fluoropolymers. So again, the process is as usual. So now the reactive neutral, they bombard the side wall. At the same time, they bombard the surface, also normal surface, and the charged ion, they bombard the normal surface, and as a result of this, the high energy of the ion, the local evaporation happens, and the normal substrate is removed. And at the same time, this is important. So now what we added? So we added fluoropolymers. Now the fluoropolymers, what they do is they will make a layer like this. So by adding fluoropolymers, a layer is formed. So during the process, a polymer layer is formed here. So because of this, my angle theta becomes 0. My angle theta becomes 0. So because of adding of the reactant, the fluoropolymers, a polymer layer is formed, and a polymer layer is formed. As a result, my theta is becoming 0. So this is very important. In the deep reactive ionic stage, the adding reactant is different. So as a result, the added reactant will form a polymer layer, and as a result, the theta will become 0. Or so theta, in some cases, I may get a theta of around 2 degree. So that it can be neglected. So what I need to do here is, so the deep reactive ion etching, so the plasma etching can produce deeper trenches than wet etching, but with tapered angle. So the tapered trenches, they are not desirable in many applications, such as micro gripper or in some electrode application. So the deep reactive ion etchers may produce deep trenches with theta equal to 0. So this is very important. So the deep reactive ion etching process may produce deep trenches with angle theta equal to 0. So DRIE, so deep reactive ion etch process, differs from plasma etching, and it produces thin protective film of few micrometer on the side wall during the etching process. So during the etching process. So now this is the layer. So what you are saying? So it produces a thin protective film. It produces a thin protective film, usually of polymer of few micrometer. So this thin protective film is nothing but this now. It's a thin protective film on the side wall. Okay, so usually thereof this thin film is produced during the process and usually a polymer film. Okay, so of very few micrometer thick. Okay, so can be aspect ratio can be 30 and with virtually theta equal to 2 degree. Okay, so now finally, what is the difference between the dry etching and wet etching? So this is very important from exam point of view. So if I take the directionality, so directionality it is good in dry etching, and in wet etching it is only for the single crystal material. Okay, if it is the single crystal material, it is wet etching, it is good. But if it is multi-layered etching, so this wet etching it is not good. So whereas under that condition I need to go for dry etching. So similarly, production automation it is good in dry etching, in poor it is poor in wet etching. Environmental impact it is low in dry etching, whereas in wet etching it is high because the chemical, whatever the chemical solution I need to dispose. Okay, so I need to dispose, I need to take very special care. So the environmental impact is high in wet etching and it is very low in dry etching. Similarly, selectivity. So selectivity is poor in dry etching and good in wet etching. And similarly, material to be etched, it is only certain materials are available for the dry etching, and wet etching I can employ for all the material. Can employ for the all the material. And equipment cost, dry etching is very expensive and wet etching it is less expensive. Why? Because the chemical solution I can easily get. So that is why it is less expensive. And dry etching, so because I need to generate plasma, I need to add reactive gases, neutrals, and all that process is very expensive. Okay, so etch rate it is very slow in dry etching, and wet etching it is very fast. And operational parameters there are many, because I need to set the frequency of the radio frequency, I mean source, radio frequency source, then selecting of reactive gases. So all that many operational parameters are there. Whereas in the wet etching there are few parameters. In the control of etch rate, it is good in case of slow etch, and it is in the wet etching it is very difficult to control. So very difficult to control the etch rate. So this is very important from exam point of view. What is the difference between dry etching and wet etching? So any doubt can clarify. Wet etching and dry etching very important. So in the dry etching, so dry etching is the plasma. So what I need to do is I need to first generate plasma, then I need to add reactive gas. So that reactive gas is nothing but Freon 12. And during this process, what will happen is there's a generation of the reactive neutral. They bombard the sidewall. At the same time, they bombard the normal surface, and the charged ion they bombard the normal surface. And because of the high energy of the charged ion, the local evaporation happens on the normal substrate, and the material will be removed. So this is the plasma etching. And the deep reactive ion etch. So what will happen is I'll get a deep trench during the process. I'll get a deep trench with some angle theta, and what I need to do is I need to make theta equal to 0, or I need to make theta as minimum as possible. For that, what I'll do is I'll go for the deep reactive ion etch. And the deep reactive ion etch, the process is almost similar to the plasma etching, but the difference is I need to add different reactive neutral. That reactive neutral is nothing but fluoropolymers. So fluoropolymers, what they do is they form a thin layer, protective layer in the sidewall. During the process, they form a thin protective layer. Process is again normal, similar to the plasma etching. The reactive neutral they bombard the sidewall and the normal surface, and the positive charged ion they bombard the normal surface. And again, because of the high energy of the charged ion, local evaporation happens and the surface layer is removed. And with an angle theta equal to 2 degree, I can do the deep reactive ion etch. And finally, the difference between the dry etching and wet etching. Any doubt you can clarify? So from exam point of view, plasma etching and deep reactive ion etch, and the difference between the dry and wet etch is very important. Any doubt? Any doubt?
No, sir.
Okay. We'll stop here. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.